Alright, so in this video lesson we're going to discuss factoring differences of squares and some terminology that goes along with them so that when you move up in your courses that you'll have been familiar with and heard these words. So first off, what is a difference of squares? Because to be able to factor one, we need to know what a difference of squares in the first place. Well, differences in mathematics, if you have difference, it means a subtraction problem. And to be a square in mathematics, it means you're a square number. So that means you will need to know your list of square numbers, which means you need to know 1, you need to know 4, 9, 16, 25, 36, 49, 64, 81, 100, and a 121 and a 144, and we'll stop there for now. But, okay, you do need to know these numbers, okay? And the reason you need to know those numbers is because all of these numbers are multiplied together by taking one number and multiplying it by itself. So to get the perfect square of 1, it's 1 times 1, the perfect square of 4 is 2 times 2, and the perfect square of 9 is 3 times 3. So we're going to have a difference of squares. So the way that this is written algebraically is we will say a squared minus b squared. And all that formula means is you're having something squared. So another thing you could have squared, so what you've learned before is that these were the numbers, okay? So the next thing you need to know is that, well, not only are there numbers, there are variables that are perfect squares, and we'll start off with those variables. So perfect square variables are going to be x squared, right? It says squared in itself. The next one that I would get is x to the fourth. And for this video, I'm not really going to go any further than that, but then you have x to the sixth. So what you need to know about variables is that perfect square variables, okay, are anything that has an even exponent. They will become perfect squares. And the reason for it is because all even numbers can be divided by 2, which means they can easily be cut into half. So what that means is to make x squared, you have x times x. How do you make x to the fourth? It's x squared times x squared. How do you make x to the sixth? It's x cubed times x cubed. So perfect square variables, you need to know, okay, are anything with an even, and the reason for it, again, is because all even numbers are divisible by 2. So you can cut your exponent into half. So with that being said, that's why we write the generic formula as a squared minus b squared, because it's generating the idea of a square minus another square. So what we want to talk about is what they factor into. So before I go ahead and I give you the actual formula for it and give you the proper names, I'm just going to go through an example and explain, how it comes to this, because it's not really, it's a shortcut only in the sense of it saves you work because you understand something. So you have to understand something in the first place to be able to do it. So let's go through and give an example instead of making this a generic conversation. So here's an example, right? It says x squared minus 16. Now, this is a quadratic. Now, it's not a quadratic that you're used to seeing. Most quadratics you're used to seeing are in the form of ax squared plus this bx plus c, in which there's some sort of middle linear term. So as of right now, you've got this quadratic term, and I'll highlight it here. So I'll highlight your terms. You've got this quadratic term here in green, and then this number here is called a constant. So in the form of the thing, of the generic formula, you've got this ax squared, you've got this c, but ironically, you're missing this middle term, this bx, okay? So with that said, I'm going to go ahead and I'm going to fill in that bx. And you may ask how I'm going to fill that bx in, but it gets filled in like this. So, use a different color here. So I use x squared, and I'm going to use plus, and how do I represent something in mathematics as not being there, but showing that it's not there, and that's what the number is 0. So that is 0x and then minus 16. And now we've gone through factoring quadratic trinomials at this point, and there was a process to that. And the process to that was, if the leading coefficient was 1, okay, you should be able to understand that there's only one way to make this, and these quadratics are going to be made by taking a linear times a linear. So I set up my two linear expressions, and the first linear expression is the x and the x, because there's only one way to make that x squared. So that first term is taken care of just by separating it. And then what we talked about is that the second part, this part here and here, okay, must be constants, because the only way to make that number through a distribution is to multiply a constant by a constant. So then this middle term, all right, is actually created by doing a byproduct, because what you'll notice is that you'll take this x and multiply that constant, and this x and multiply that constant, right? So going through this problem, what we have here, all right, is we need to figure out these two constants so that we can be done. Well, the way you do that is by figuring out what do you multiply together to make negative 16, okay? That will then add to make 0. So when I write down my possibilities, the first one is positive 1 times negative 16. Well, if you add those two together, that's negative 15. That's not going to work. And if you just switch the signs to negative 1 and 16, all that does is make it into a positive 15. So then you can go on to the next, which would be 2 and negative 8. That's not going to make 0, because the way you make 0 is the additive, okay, is the additive inverse rule. So you have, when you add opposites, you get 0. So 16, the reason it's nice is because 16, while you can use these other numbers like negative 2 and say positive 8, okay, to multiply them together to make 16, if we keep going, what you'll get here is eventually you get 4 times negative 4. And 4 times negative 4 creates, okay, when you add them together, it creates the additive inverse property. And the additive inverse property states that if you add two numbers that are opposite together, you will create 0. And that's what our goal is here. So in this problem, it factors into plus 4 and minus 4. Now, with that being said, I don't want to have to do all of this work. And what you'll see here is that no matter what I do, right? So no matter what number I change this to, so long as my first number is a perfect square, and so long as that second number is a perfect square, and I'm subtracting, you're always going to be trying to make 0 in the middle. And if that's the case, your constant number, whatever it may be, or your variable number, okay, you could have a difference of variables, all right? What you'll know is that there are two things that are going to be opposites to multiply together, all right, to make 0. So what this is called, all right, is called a difference of squares. And because a difference of squares, what we had was a squared minus b squared. Because this phenomenon always occurs that we're trying to make this bx into a 0, all right, what you end up getting, okay, in the bottom of my screen here, I'm going to write out the formula, is you end up getting this, this thing that always happens, which means if you take a look at my factored pair here with all the work in it, okay, it says x plus 4 and x minus 4. So notice the middle sign, okay, is just opposites. So they have an inverse operation to one another. So the inverse operation of plus and subtraction, they undo another. So that is what is called, okay, a conjugate pair. So what you'll need to know is, and you may hear your teacher say it, but all differences of squares factor into conjugate pairs, which means the first term in each group is the same. And the second term in each group is the same. The difference will be is that one of those groups will be adding the two terms and the other group will be subtracting the two terms. So when you have groups that are the first term and second term are all the same, these are what we call conjugate pairs. Okay? And conjugate pairs, what you need to know, when multiplied together, will always make a difference of squares. So that's the big, long explanation. But let's just go through a couple more examples. And what we're going to do is we're just going to simply try to figure out what value would exist for the conjugate pair. So let's just go on to another example. Okay, next example here. It says 2x squared minus 25. The first thing that's important to note is that I notice that it's subtraction, because this only works for a difference of squares, okay? The name of the shortcut has in it what must be going on within the expression. So difference, so subtraction, good first. Okay, the second thing I notice is, okay, 4x squared. So to figure out the conjugate pair, because what I'm trying to do, okay, is I'm trying to place a number here and here that's the same, and then a number here and a number here that are the same. So in blue, this blue underline, I'm trying to make something the same, and then switching this red underline the same. So the red goes with the first term, and the blue goes with the second term up top. So what I'm trying to figure out is what multiplies by itself to make 4x squared. So the x squared is kind of simple because it's got to be an x times an x. So we separate those as normal. Now the 4 is why I said in the beginning of the problem, you need to know what are going to be the things that multiply together to make your perfect squares. And the way you make 4 is by doing 2 times 2. So in this case, you cannot just pick 1 and 4. All right, it must be 2 and 2. So you have 2x and 2x, because what to make a conjugate pair is your terms must match, except for the fact one is adding and one is subtracting. So then we go to the next one. So for this 25. So what two numbers that can be the same can multiply together to make 25 is 5 and 5, except for when we do this problem, one will be plus and then one will be minus. And then you're now done. So the goal to this is recognizing, one, that it's a difference, and two, that this and the first number and the second term are going to be perfect squares. So again, this factors into 2x plus 5 times 2x minus 5. And again, these are what we call conjugate pairs. Okay, so conjugate pairs are just an important name. You're going to hear it often when you're in your Algebra 2 class. On to the next example. Okay, so the third example here. So it says x squared plus 9. Now, this is an easy one to get caught up on, because you see x squared and everybody goes, I know how to make x squared. And they go x, and then they go x. And they go, wow, I know how to make 9. It's 3 times 3, minus plus, and then they think they go on. And the problem with this one is that this doesn't work, okay? And the reason it doesn't work is because the only way to make positive 9, okay, while that is a perfect square, this says a sum and not a difference. And in the real term, okay, in the real set of real numbers, the way you make positive 9 is by either taking positive 3 times positive 3 or negative 3 times negative 3. And unfortunately, positive 3 and positive 3 are not opposites, nor is negative 3 and negative 3. There aren't opposites, they are the same. So for this problem, okay, you get x squared plus 9. And unfortunately, it's not a difference of squares. It's a sum of squares, and you'll learn how to factor this in Algebra 2. But for you right now, what you're going to write is this word prime. And what the word prime means is that something is unfactorable. So if a quadratic, as you see it, you can't factor it, we just say that the quadratic at the time is prime. It is a prime quadratic. So I hope that helps, but for this one, I just wanted to interject one that wasn't a difference of squares so that you know when not to do it, and you just don't think just because you see two things, you always have a difference of squares. On to the next one. All right, so now example 4. So example 4 amps up the game a little bit, because this is what we call a difference of terms. So a difference of terms at this point, okay, I have to look at it. And when factoring quadratics, I just want you to know, I just want to interject a problem. The first thing we should always be looking for is a GCF, okay? So the first couple examples, I just went over the idea of just the skill for factoring a difference of squares. Now, whenever factoring, you should totally always be looking for a GCF. And a GCF just simply is something that knocks down each term, whether it's a degree, whether it's a multiplier, but you're looking for something that's in common between the terms. So if I take a look at this first term, it says 3x squared. And if I take a look at the second term, it says negative 12. So at the end of the day, what I'm looking for is, would I be able to, if I wanted to divide, would I be able to divide something away from the first term that I could divide away from the second term? And the answer is yes. And the reason for that is because if you look at 3 and you look at 12, 3 and 12, okay, have a common factor, which means that if I were to write the factors of 3, which are 1 and 3, and if I were to write the factors of 12 are 1 and 12, okay? 2 and 6 and 3 and 4. And what I mean by having a common factor is they match identically. So that means what I can do is I can think about this problem as dividing away a 3. Now, unfortunately for factoring, it means the reversal. To factor something means to write it as the things that we are using to multiply together. So I have to be thinking about, okay, what number could I use to multiply to make 3x squared that I could use to make negative 12? And that's why writing out the factors sometimes is helpful to find out the greatest one. Because if I said that this problem really was, from the get-go, 3 times x squared minus, okay, so 3 times what makes 12, and that's negative 4. I now have a problem, okay, that was just multiplying by 3. So this video is about differences of squares. And if you notice, what I now have is a problem where I'm just taking a number and multiplying it by a difference of squares. However, the video also is about factoring. So to factor means to continue to write it out as a multiplication problem. So x squared minus 4, the question is could you multiply something together to make it? And you should know, hopefully at this point, that to make a quadratic, you must take a linear expression times another linear expression. And the question then becomes can I take this 3 and break this next expression into a linear times another linear? And the answer to that inevitably is going to be yes for this problem. And the reason for it is because x squared is a perfect square and the number 4 is a perfect square, and they are connected by subtraction, which means that when I place the 2 here and the 2 here, one of them will be positive and one of them will be negative. And again, these two things right here, when you're placing them and they're identical terms, except one says plus, one says minus, they are called conjugate pairs. So you may hear your teacher often say that, hey, what do differences of squares factor into? They factor into what we call conjugate pairs. But inevitably, my final answer is now here. Once you make your difference of squares for these problems, you're then done. So while this is the upper level of the problems out of Algebra 1, for most teachers, I do have one more challenge problem that you could go through, and I'll just show it to you very quickly. If you don't understand it, I completely understand, but I'm going to go through this kind of quickly for the sake of time. So here we go. So here's your challenge zone, right? And I talked about types of variables that were perfect squares, that if you notice you have an even exponent, that is going to be a perfect square. And then we have 16, which is just a number. So here's my challenge zone, right? So 1, I have 2 terms. The first term is a perfect square variable because the exponent is even. So it's a memorization problem, just so you know that it is divisible by 2. So 4 is divisible by 2, which means I can break it down into 2. And then we have a subtraction. So again, this whole idea of subtraction plays a part. So the first group, all right, becomes, well, if I broke x to the 4th into 2, it becomes x squared and x squared. So that's the first step. It's figuring out what thing multiplies by itself to make something the perfect square. And in this case, the 4, you're literally dividing it in 2. So if you separate this into 2 even groups, you get x squared and x squared. So that's the easy part, right? And then you have 16. And then 16 simply becomes the 4 times the 4. And one could be positive and one could be negative. And a lot of people would stop here because they think they're done. But the goal in factoring, remember, is to continue to break apart things into multiplication as far as you can. All right? So here we go. So if I take a look at this, x squared and plus 4, well, there's 2 terms there and one's plus. So I don't have a shortcut at this point for sums of perfect squares. But if I look at this second group, it's a x squared, and it's a subtraction, which means it's a difference, and then 4, which is also a perfect square number. So this first group of x squared plus 4 stays put, but, okay, this second group of x squared minus 4 can be broken down into 2 linears. So, and the linears they break down to are going to be this x and 2's, and one will be positive, one will be negative. So I have what is called a prime quadratic here that is going to be multiplying these two conjugate pairs. Okay, and then this will be my final answer. I can't break anything down farther into a multiplication problem, but needless to say, the goal for this one is to just see it in case you could get it from your teacher or not, but it's just meant to be a challenge one so that you understand a little bit farther and the idea of when I talked about in the beginning of the video for perfect square variables. So I hope that helps. Let me know and reach out to me if you have questions or post comments on the bottom of this video.